Welcome to the eighth part of mechanical properties of fluids. In this, you will learn about some cases of Bernoulli's principle and about the speed of efflux, or you can say Torricelli's law of efflux. Bernoulli's equation in different situations. Consider the first situation when a fluid is at rest. That means velocity is 0. So by putting the value of velocity 0, you will get P1 plus rho g H1 equals to P2 plus rho g H2. Or simply P1 minus P2 is equals to rho g into H2 minus H1. And this one we have studied in the Pascal's law equation also. Now consider the case when the pipe is horizontal. Means H1 is equals to H2. That means no potential energy by the virtue of height. So from Bernoulli's equation, P1 plus half rho V1 square plus rho g H1 equals to P2 plus half rho V2 square plus rho g H2. By putting the value of H1 equals to H2, you will get P plus half rho V square equals to constant. Here, there are some points to be noted that in applying the energy conservation principle, there is an assumption that no energy is lost due to friction. But in fact, when fluid flow, some energy does get lost due to internal friction, and this arises due to the fact that in a fluid flow, the different layers of the fluid flow with different velocities. These layers exert frictional forces on each other, resulting in a loss of energy. And this property of the fluid is called viscosity, which we will study later on. The lost kinetic energy of the fluid get converted into heat energy. Thus, Bernoulli's equation ideally applies to fluids with zero viscosity or non-viscous fluids. Another restriction on application of Bernoulli's theorem is that the fluid must be incompressible, as the elastic energy of the fluid is also not taken into consideration. But in practice, it has a large number of useful applications and can help explain a wide variety of phenomena for low viscosity incompressible fluids. Bernoulli's equation also doesn't hold for non-steady or turbulent flows, because in that situation, velocity and pressure are constantly fluctuating in time. So you can say all these are the limitations of the Bernoulli's theorem. Now, application of Bernoulli's theorem. Firstly, we will find out the speed of efflux. Efflux means fluid outflow. And Torricelli discovered that speed of efflux from an open tank is given by a formula identical to that of freely falling body, which you have studied in the kinematics. For this, consider a tank containing a liquid of density rho with a small hole in its side at a height y1 from the bottom as shown in the diagram. The speed of efflux v1 from the side of the container is given by the application of Bernoulli's equation. The air above the liquid whose surface is at height y2 from the bottom of the tank is at pressure P. From equation of continuity, V1A1 must be equals to V2A2, where A1 is the area of the topmost of the tank. So from this equation, V2 will be equals to A1 divided by A2 into V1. If the cross-sectional area of the tank A2 is much larger than that of the whole, as it is clear from the diagram, and you also by your practical knowledge, you know that the tank on the roof of our house has very large area as comparison to the area of the tap. Then we may take the fluid to be approximately at rest at the top of the tank. That means you can consider V2 as 0. Now, by applying the Bernoulli's equation at points 1 and 2 and noting that at the hole, pressure P1 is equal to atmospheric pressure denoted by PA. So, PA plus half rho V1 square plus rho G Y1 equals to P plus rho G Y2, or half rho V1 square equals to rho G Y2 minus Y1 plus P minus PA. Let us take Y2 minus Y1 as H. Means it is the height from the top of the tank where the liquid is there up to the hole in the tank. So half rho V1 square will be equal to rho GH plus P minus PA. And from this equation, you can calculate the velocity V1, and that will be 2GH plus twice of P minus PA divided by rho under the root. Now, if the tank is open, that means the pressure at the top is also atmospheric pressure. So it will be only under root 2GH. When P is very greater than PA, then 2GH may be ignored. And the speed of efflux is determined by the container pressure. Such a situation occurs in rocket propulsion. On the other hand, as I have told you already, that if the pressures are same, then the velocity V1 will be equals to under root 2GH only. And this is the speed of a freely falling body and is known as Torricelli's law.